So the first speaker is Edoardo Provenzi from University of Bordeaux, and he will speak about some interesting connection between the geometry of quantum mechanics and the space of perceived colors.
Okay, thank you very much. I will present this on the behalf of my dear colleague and friend Michel Berthier of the Université de La Rochelle. Okay, so the outline of the talk is this. First of all, I will introduce Schrödinger's axiom about color perception, and then a beautiful model called a Resnikov model. And then I will talk about the use of Jordan algebras and the connection with quantum mechanics. So let's start with Schrödinger's axiom. In 1920, Schrödinger did something that can be thought as an analogous of what Maxwell did for the electromagnetic field, because he collected previous results about color and he introduced one axiom by its own, exactly as Maxwell did. Maxwell used differential equation, and Schrödinger used axioms, but it's exactly the same. And I will not display all the axioms of Schrödinger, we don't need them, but I will fix only on two axioms which are particularly important for this talk. And then, after his beautiful work, the CIE, Commission Internationale de l'Éclairage, in English, International Commission of Illumination, started to work on a much more industrial-related application to color. And unfortunately for us, who like geometry and theory, the color spaces that came out with the work of CIE are only heuristic and not precise at all at a mathematical level. There is a very noticeable exception in the second half of the 20th century. That is the beautiful work, in my opinion, is a masterpiece. I strongly suggest you to read it if you don't know it yet. It's called The Differential Geometry and Color Perception by Resnikov in 1974. This work has been absolutely ignored by the community of colorimetry. The reason is that, imagine 1970s, it was the period when physicists developed the Standard Model, and so Lie group theory was the zeitgeist, and of course colorimetrists didn't know anything about Lie group theory. So it was totally ignored. It was thought as something that is pretty incomprehensible, but nowadays with my colleague and other people, we are rediscovering what Resnikov discovered and wrote in 1970s. Okay, so let's start with Resnikov model. It is very important to describe the setting where Resnikov model works, because it is a very, very simple setting, and it's not at all what we are seeing in this moment. This is a it's called natural scene, and colorimetry is not based on experiments on natural scenes. Believe it or not, even nowadays, the only experiments that we do in colorimetries are slight modification of this one. You have a uniform background, and you have a simple color stimulus at the center of this uniform background, and you are seated in a control condition without any other light. Okay, this is how colorimetry, standard colorimetry works. And we don't consider the neurophysiological behavior of the human visual system. We just consider it as a black box, an internal transducer. And the result of this black box is what we call a perceived color that is induced by this light stimulus. And also, we consider an ideal average observer who has 3 retinal cones. You know that there are colorblind people and they only have 2 or 1 retinal cone that works. In standard colorimetry, we consider persons with 3 retinal cones that are working as an average person. So let me introduce some notation. With the capital lambda, I will denote the spectrum of visible wavelengths. In general, we take the minimal visible wavelengths with 380 nanometers, and the maximal visible wavelength is 780 nanometers that correspond to deep red to violet. And it is standard to denote the space of physical light, visible spectra, with L2 of lambda. These are L2 functions defined on lambda, and they take positive values. They correspond to the intensity of these radiations. We introduce an equivalence relationship that is called metameric equivalence. We consider two light spectra as being metameric equivalent if they generate the same perceived colors. Imagine we have two different spectra, but when we integrate the spectra with respect to the sensitivity curves of these three cones, even if they are different, they can generate, and they generate, actually we have many spectra that are metameric, the same responses with respect to the three cones. We must consider, of course, these two spectra as equivalent with respect to perception. Okay, the quotient space pi L2 plus lambda with respect to metameric equivalence is called the space of perceived colors in this very restrictive setting. And of course, this is very difficult to characterize mathematically and to use it for industrial application. This is why we must represent it in a way that can be used for application and to manipulate it and analyze it. In order to do that, it is common to introduce the vector space V spanned by pi with a canonical linear structure. And you might be surprised to see real coefficient and not only positive real coefficient. This requires an explanation. In general, in colorimetry, what we do in order to compare colors is to use a bipartite field. So we still have this homogeneous background. We throw a light on the left of this bipartite field, and we try to match the light, let's say, to fix the ideas on the left side, with a spectra on the right side. When the edge between the two lights disappears, it means that we have color matching, okay? So equality means color match in this sense. Plus, I'm describing the algebraic structure. Plus means that we are superposing physical lights. And minus, this is the tricky point, minus means that we are not superposing lights on the same side, but we throw light on the other side of the bipartite field. If you want, this is I just discovered that this through this beautiful little book. This is related with tropical algebra developed by French and Brazilian people. This is why French people call this tropical algebra. And multiplication, yeah, it's true story. Multiplication by alpha is just modulation of light intensity. So this is the algebraic structure that corresponds to this vector space. I wanted to tell you about it for just 30 seconds because it's quite peculiar. Okay, so let me now go to, you wanted to take a picture? Ah, okay, please. Okay, okay, so let me now take the two axioms, Schrodinger axioms that are important for this talk. And the two axioms come from observations by Newton and Grassmann. Yes, it's the same Grassmann that invented modern linear algebra. And you will see that many mathematicians that you know and you adore are quoted in this talk. They all studied color perception. And Newton's observation is that if we multiply a perceived color by a positive constant, then we still get a perceived color. And Grassmann noted that if we do perform a convex combination, we still have of two perceived colors, we still have a perceived color. So it is axiomatized by Schrodinger that pi is a convex cone. And the dimension of this cone is 3 for an ideal trichromatic observer. Okay, what Resnikov did was to, I don't know if you can see it, I hope so, but was to start with this observation to introduce a new axiom. So when I created these two pictures, I used exactly the same physical color here and here. But as you can see, depending on the background, our very perception is quite different. This is a bright green, and this is yellowish. Do we perceive it? Okay. So what's the lesson that we learn from this? The lesson is that if we change the background, our color perception changes. And Resnikov has the brilliant idea of putting some math on this observation. And so he said, quoting almost literally, if X is a perceived color, then it can be turned into a not too different color Y by a background change, and the process is reversible. So he introduced the group of background changes like this. So orientation preserving, invertible endomorphism, of V, which preserve pi. And this is the specification of this group. You may be surprised, as I was, to see linear transformation. Okay? I will turn back to this point, to this very, very important point in a few minutes. But for the moment, let's consider that Resnikov assumption is correct, and let's see the consequences. Okay, so he thought that the local homogeneity of pi with respect to this group of transformation could lead to global homogeneity just by using a very elementary argument based on convexity. And in fact, he postulated that the entire space pi, is globally homogeneous with respect to the action of this group. And he analyzed the consequences of this axiom. I don't want to enter in details. You know these details much better than I do. And I just say that if we consider the stabilizer K, then we have this isomorphic identification of pi with this quotient group with respect to K. And if we fix the determinant of this linear transformation to be 1, and we use the fact that pi is preserved with respect to this kind of transformation, then in particular we have this isomorphic identification of pi with R plus cross SL pi on K. And of course S means that the determinant of G, this transformation G, is 1. Okay, so the argument, you can see the details in his paper. The argument that Resnikov used in order to single out the possible structures of pi is very elegant, and it's based solely on dimension, a dimensional argument. So the idea is this. Since the dimension of pi is 3, this implies that SL pi is a subgroup of SL3R. And so we have this constraint here that reduces to this constraint here. And by using standard result of harmonic analysis of semi-simple and nilpotent Lie groups, and which are not trivial but standard, he proved that this inequality here implies that there are only 2 geometrical structures that are compatible with this constraint. The first one is well known, and it was well known to colorimetrists at that time. It's called the Helmholtz-style space, and it's just the cross product of R plus with itself 3 times. And all the physical devices that we use nowadays are based on this space: RGB, XYZ, LMS, etc., etc. So this is nothing new. What is new and what has been ignored until now is this space here. And this space is very important, and as I try to convince you, we believe nowadays with my colleague Michel that this is the correct color space with respect to human perception. And as you can see, it's the cross product of R plus with the Poincaré-Lobachevsky two-dimensional space of constantly negative curvature. So for the first time, we introduce the concept of curvature in colorimetry. And of course, there are many practical representations of this space. For this talk, I will use only this one, the 2x2 real positive defined symmetric matrices with determinant 1. And let's see how we can interpret from a colorimetric point of view this geometrical structure here. Okay, first of all, it is absolutely natural to search for a group invariant Riemannian matrix on pi, since it is the action of the group that generated this kind of structure. And of course, the group invariant Riemannian matrix are defined like this. And Resnikov proves that if we consider the first geometrical structure, then we turn back to another metric that is well known in colorimetry called the Helmholtz-Stiles metric. And the other one was completely new at that time. And nowadays, with the explosion of geometrical theory of information, we know that this, with this identification for the quotient group, is equivalent to the Rao-Siegel metric. So nowadays, we know very well this metric. At that time, no. Okay, at least it wasn't that spread in the scientific community. So one way to test the theory was, for Reznikov, was to consider brightness perception. What is brightness? Brightness is the difference. Brightness is the difference between physical light. The color perception induced by physical light that only differ for a constant, a positive constant. Okay. So it is in this framework. It is calculated just by an integral over a geodesic arc connecting x and alpha x over one of the two Riemannian metrics that I defined before. And surprisingly, for both metrics, what we have is that the brightness difference is proportional with different proportionality constant to the logarithm of alpha. And this is well known to be the so-called Weber-Fechner's law. So this was very important that both metrics agreed with Weber-Fechner's law, because this law is a very well-established perceptual law. So if they predicted something else, okay, we should have thrown the model in the garbage. And of course not. But the difference between the prediction of the two models, and this is very important, is what the two models predict with respect to surfaces of constant brightness. And for the first model, these surfaces are are flat. And for the second model, these surfaces are hyperboloids. And unfortunately, this paper is not, has not been published yet, but I have a very good friend in Grenoble, David Allison, who did some novel psychophysical experiments, and he proved that for color perception by humans, surfaces of constant brightness are indeed hyperboloids and not flat surfaces. So we believe that this is the correct structure, and the second structure is the correct one. But there are many other indications that the second structure is the correct one. I just underlined that you see Ilmaz, who was a colorimetrist, but Weinberg also worked on color perception, and he sorry, this doesn't, okay. And he also predicted in a quite involved model that I still don't understand that surfaces of constant brightness for human perception were hyperboloids. Okay, let me now, 5, oh, wow. It's running very, very fast. So Reznikov, let me turn back to the linearity hypothesis. Reznikov, in a subsequent paper, said that the strongest hypothesis about the group of transformation acting on pi is linearity. In fact, there is no reason why those transformations should be linear. But without their linearity, this whole model cannot exist. This is why, with my colleague Paola Iocomussi from the National Meteorological Institute of Turin, we are developing a psychophysical experiment in order to see if these background changes are really linear or not. We are still in progress. It's I don't know anything about. I didn't know anything about psychophysical experiments, and I'm learning that it's quite difficult to realize. Okay, let me very fast go forward the Jordan algebra use. Okay, I will be very, very fast. Jordan algebra is a vector space with a commutative bilinear product that in general is not associative, but always power associative thanks to this identity. And in particular, we are interested in so-called formally real Jordan algebras, and they are the algebras that behave like this. In these algebras, there is a partial order that allows us to define the positive elements, and we can also always define an inner product like this just by considering the trace of the endomorphism induced by any element simply by the Jordan multiplication on the left. Okay, so there are two basic theorems that I have to quote. The first is the Jordan von Neumann-Wigner classification of formally real Jordan algebras. They are just a direct sum of simple ones, and the simple ones are written here. Either n by n Hermitian matrices with entries in the real complex or quaternions. For 3 by 3 matrices, we can also allow octonions. The Jordan product is this one. And the other simple formally real Jordan algebras are spin factors with this Jordan product here. Okay, the other theorem refers to cones. And if we consider this set here as the set of positive elements, we take the interior. This set for formally real Jordan algebras, not for everyone, but for formally real, this is a convex cone. It is homogeneous. It is self-dual. It is isomorphic to his dual. It is regular. In general, an open, convex, homogeneous, regular, self-dual cone is called a symmetric cone. And the other way around is contained in the Kocher-Wimberg theorem. Each symmetric cone is isomorphic to the positive cone of a certain formally real Jordan algebra. And what is important for us is that if we consider Jordan algebras of dimension 3, then the only possible symmetric cones that we came out with are exactly the two symmetric cones that have been found by Reznikov. And so, without considering the specific action of a group, using the theory of Jordan algebras, we can get exactly the same result. And we don't have to bother if those transformations are real or not. Of course, this is important to close the circle, but we obtain the same result by passing to Jordan algebras. Okay, I'm going very, very fast because I don't have time, and I will have to skip this. But thanks to Jordan algebras, we had the idea of considering something that was related with quantum mechanics, because if you take the algebraic formulation of any physical system, but in particular quantum mechanics, then you consider the observables as elements of a certain algebra of observables. And for us, it was important to try to define the colorimetric attributes from the very properties of these observables in the Jordan algebras. And we did it. What we proposed was to consider density matrices in formally real Jordan algebras, which are positive elements with trace 1, and to describe pure and mixed states through these density matrices. Of course, this can be done by considering the von Neumann entropy. And in particular, well, of course, when the von Neumann entropy is minimal, we have the maximal possible information on the state defined by density matrix. And when it's minimal, and it can be described by the unity element of a formally real Jordan algebra divided by its trace, then we have the maximal possible entropy of the state. And how can we use this information in order to characterize the chromatic attributes of a color? By considering three-dimensional Jordan algebras, formally real, which are either this or this, which are isomorphic through this. And it is possible to prove that each density metric in this case can be written like this. And in polar coordinates, they can be written in this form. And as you can see, the state of maximal ignorance is just the identity matrix divided by 2. And the other matrices here describe pure color as the angle turns between 0 and 2 pi. This is reminiscent of what happens in qubite in quantum mechanics, spin 1/2 particle. But we call this a rebyte, a real qubite, because we are considering a real algebra and not a complex algebra of Hermitian matrices. But again, just a second, the states are in the two-dimensional block body. Pure states lie on the boundary, and the maximal entropy state is in the center. So this led us to the proposal of measuring the saturation of a color as a von Neumann entropy, the achromatic value of a color lying at the center of the block disk, and the pure states lying and distributed along the perimeter. If I don't say this, it's completely meaningless for me. why we think that this is a nice and very promising description of color perception. Because we can rearrange the description of density matrices like this. And look at this. Here we have the maximal entropy state. And I put it as gray because the maximal entropy state is what we call the average gray. And there is no color information, so it's gray for us. Here you have the opposition between pure colors, and here is the same. And the codification of achromatic colors plus the opposition of two colors is well known. And there are ganglion cells in our retina that codify color information arriving from the cones exactly like this. And another way of recovering this result is by using principal component analysis on a set of images, of color images, and you will find exactly that the eigenvector of the covariance matrix are a chromatic value plus opponent colors. But this is a posteriori description. In our model, it is an a priori and naturally embedded description. This is why we believe that this framework is possibly the correct one to describe color perception. And it's done. Okay. Sorry if I was too long.
We have time for two questions. Then, please.
Yeah, well, very beautiful work, very beautiful work. So, I think I'm very happy to see that you actually get the color circle as the theta,
yes.
right? So now here's the question. So you have the background and the foreground, right?
Yes.
So basically, the two colors, the colors of background and the color of the foreground, they both form color circles. So the topology of that is a torus.
I'm going back to this.
Yeah.
Okay. What do you call color of the foreground and color of the background?
So well, you have the background and then you have the disk.
Yes.
See that, right? So you have two, and each of the color eventually you have a color circle with this, right? So then you have a color. You have two S1 cross S1, which is torus.
I don't think that is correct, but I will be happy to discuss with you because it's not like this. But
okay.
Can we discuss later?
Sure. Yeah.
Okay, it's a very long discussion.
Okay.
So the question.
Yes, the model you propose is an interaction in between background and color. Can you imagine the perceived color is sometimes depending on more complex
yes.
stuff? So basically, can you imagine generalizing?
Exactly. Thank you a lot for the question, because we are starting a PhD thesis about this generalization, and we want to use fiber bundle theory in order to generalize this. This is the isolated condition. The real condition must be, this case, bundleized, if you want, principal fiber bundleized, and so we will get information for each different fiber will describe one specific point in interaction with his background. But okay, did I answer your question?
Yeah.
Okay, so we want to extend this with principal fiber bundle theory, but I would love to discuss with you more about this.
Okay, so let's thank you.
Okay, thank you a lot.